Section 3.2 is about analyzing graphs of polynomial functions. So the first thing that we will discuss about this section is what is a polynomial function. Now, according to the definition, a polynomial function is a function that basically, I'm just going to go straight to the point based on what the definition says. It is a function that consists of exponents which are non-negative integers. Okay, of course, and real coefficients. Okay, real coefficients. These are just coefficients, which are the numbers in front of the variables, so they have to be real numbers. But the main thing that makes a polynomial function is that it is an expression, it is a function that contains only non-negative integer exponents, meaning 0, 1, 2, 3, 4, and so on. Now, this word right here, degree, means the highest power of that polynomial function. So the highest power is called the degree. Also, the last thing is that the number that is in front of the variable with the degree, in other words, the number in front of the variable with the highest power, is called the leading coefficient. Okay. Now, let's go ahead and talk about this first function and determine if this is a polynomial function. The question says, determine if this is a polynomial function. If it is, state its degree. Now, if we look at the degrees, at the exponents, at the powers of this polynomial, of this expression, of this function, there are 7, 4, and 3. All of them, as we can see, are non-negative integers. And that's basically what we need to have in order for this to be a polynomial function. As long as the coefficients are real, these are real coefficients, and the exponents are non-negative integers, then we can say that yes, g of x is a polynomial function. Also, we need to identify the degree. So right here, the degree of this polynomial, remember, degree means the highest power of the polynomial. The degree is going to be a degree of 7. Let's do the same thing for the next problem. We're going to determine if this function given right here is a polynomial function or not, and then we're going to identify its degree if it is. Okay. Now, if we look at the powers, this one is a non-negative integer, this one is a non-negative integer, but if you look at this last one, this one, first of all, we need to move that x back to the top. If we do that, remember from the section about radicals, that is going to become a 5x to the negative 1 power. Whenever we get the reciprocal, that's going to change the exponent to a negative. It's going to change the sign of the exponent. So, if you look at this one is a negative integer, right? And if we have a negative integer on the exponent, that automatically tells me that this is no, h of x is not a polynomial function. Okay. This one, in fact, when you have x on the denominator of the function, that one has a name, and it's called rational function. Remember, the word rational means fraction. Next, now we're going to discuss the shapes of polynomials. These are the graphs of polynomials, some of the characteristics that you need to know about them. And there's basically 2 characteristics that need to be known about polynomials. The first one is that polynomials are smooth and continuous curves. By smooth, it means that it contains rounded curves, and continuous means that it can be drawn without taking off the pencil from the paper. Or, in other words, continuous means that it keeps on going from negative to positive infinity as well. So, examples of polynomials that will be smooth and continuous, we know it is this one. That one, you see, it's continuous because it keeps on going, and it is a smooth curve, meaning that it is a rounded curve. Likewise, if we draw this one, That one is a smooth and continuous, so it has a smooth curve and it's a continuous curve. Also, we can say this one is a smooth and continuous. It has rounded curves, and it can be drawn without taking off the pencil from the paper. It continues. It keeps on going on both sides, and so on and so on and so on. Also, I can say this is a polynomial function. It has rounded curves, and it is a continuous curve. Okay. Now, something about special that you can see about these functions. It doesn't matter how it looks like. I can have many smooth and continuous curves, but all of them have very similar shapes. Meaning that either, as you can see, both ends of the polynomial, either the graph looks kind of like a U shape, or the graph looks kind of like an S shape. Okay, so basically this is a double U, which is basically similar to this one. This one is like a double U facing down, which is similar to this one. Now, each one of the polynomials have their own families. Okay, there's only two types of families that we're going to talk about on polynomials, and that is going to be called the end behavior. Okay, the end behavior basically determines the shape that the polynomial is going to take on its ends. And as we can see, the graphs on its ends, they have basically kind of the same outcome. Okay, so whether both ends go up, or both ends go down, or one end goes up, the other one down, or the other one goes up and the other one down. So it's basically kind of similar situations. That's what the end behavior, what happens on the far end, to the left and to the right. Okay. Now, this one is going to be called the leading coefficient test, and the leading coefficient test basically determines what the end behavior of the polynomial is going to be. Now, there are two types of behaviors. One of them is for degrees, which are odd. Okay, both of them are going to look like an S shape. Just like think of x cubed. The shape is going to be similar to that. And the S shape can go into different directions, whether it increases from left to right or it decreases from left to right. So in this particular cases, how do we know the difference between the two? This one happens when the leading coefficient is positive, and this one happens when the leading coefficient is negative. So the S shape goes up from left to right if I have a positive leading coefficient, of course in conjunction with my odd degree. This one happens that if we have a negative leading coefficient in conjunction with an odd degree as well. The left end, you see that it goes up, the right end goes down. Okay. Now, on the other scenario, we have a case in where the degree is even. So if the degree is even, there's two things that can happen. Whether the two ends of the function go up or the two ends of the function go down. So it has the same behavior on both sides. So if the leading coefficient is positive and the degree is even, then both ends, left and right, are going to increase. And if the leading coefficient is negative and with an even degree as well, both ends of the function are going to go down. Okay, that's called the end behavior. What happens on the far left and the far right? So we're gonna use some words. If the graph goes down, like over here, we're gonna use the word false, and if the graph goes up, we're gonna use the word rises. So, let's take a look to this first example. Use the leading coefficient test to determine the end behavior of the graph of this function. We have 4x to the 5th power plus 6x to the 3rd power plus 4x plus 5. So, based on the degree, if we look at the degree, this degree, it is an odd degree. So we know by odd, it's gonna look like an S shape. And we can see also that the leading coefficient, it is a positive leading coefficient. Okay, so if it has an odd degree and a positive leading coefficient, this is kind of like the shape that we're gonna see on that function. The left end is going to decrease and the right end is going to increase. So this is how we explain the end behavior. So we're going to say the following, that the graph of f of x using the words falls and rises, we're going to say that on the left side, it falls on the left, and on the right it's going up, so we're going to say and rises on the right. And this is how we describe the end behavior of a polynomial function. Now, we're going to talk about the zeros again. Now, remember, what are the zeros? The zeros are the x-intercepts, the solutions, the roots. That's what it means by this. X-intercepts, solutions, roots. Those are the different words representing the x-intercepts. Of course, real roots. Okay. If a polynomial function, if f is a polynomial function, then the values of x for which the y value is equal to 0 are called the zeros of the function, which are also called roots or solutions. Any value for which the y value is equal to 0, it is called an x-intercept or a zero or a root or a solution. Now, we're going to talk about something very important of zeros of polynomials, and that is in polynomials, which is called the multiplicity. Okay. Now, what does it mean by the multiplicity? So I'm going to give you a very easy definition to remember multiplicity. Multiplicity means basically how many times does a factor repeats on my polynomial equation, on my polynomial function. So, and basically it tells you this: if a factor or if a zero has even multiplicity, meaning that, for example, this is the factor x minus r. If I solve for x, remember you get x equals to r, which is what it's saying here. If r is a 0, so if you have a factor of even multiplicity, meaning that it is going to repeat an even number of times. For example, I can see the factor being repeated 2 times, or the factor being repeated 4 times, and so on and so on and so on. So when the factor repeats, I'm going to put right here an even number of times. Then when the graph gets close to this number r, the graph is going to touch the x-axis and turn around at r. That means the following. Let me give you a little concept of this definition, a little picture. Let's say this is r right here, and let's pretend that the graph is coming from above. If that r repeats an even number of times on the equation, then when the graph gets close to this r, it is going to touch at that point, but then it's going to turn back in the same direction that it came from. That's what it means by touches and turns around. Now, on the other case, it tells me right here, now if I have a 0 with odd multiplicity means that that factor is repeated an odd number of times. So x minus r times x minus r times x minus r 3 times, or x minus r just 1 time, or 5 times. If a factor repeats an odd number of times, then when the graph, like right here, let's say this is r, okay, when the graph gets close to that r, let's pretend it's coming from the top, when it gets to that r, it's going to cross the x-axis to the other side. Okay, that's what it means by crosses the x-axis. So if a factor, once again, has an odd multiplicity, then the graph is going to cross the x-axis when it gets close to that number. So let's go ahead and answer a couple of questions on this. So we're going to do this problem. We're going to find the zeros of this polynomial function, and then we're going to state the multiplicity of each zero and say whether the graph crosses or touches the x-axis at each one of those zeros. First of all, to find the zeros, we can find them by setting the y equals to 0. So to find the zeros right here, what we have to do, we have to factor this polynomial equation. So to factor it, remember that the first step in the process is to find the greatest common factor. Now, all of these we can factor an x from all of them. So we're going to take out that x, so we're going to divide that x from all these terms, and we're going to take it to put it on the outside of the expression, and that's going to give us x squared minus 4x plus 4, which is what's left. Then, the process that we use to factor a trinomial is that we're going to multiply a, which is 1, times c, which is 4. So we see, remember what we mentioned, that the a, when it's 1, is not going to make a difference, right? So basically, we just need to get the factors of 4, which is two numbers that when multiplied give me 4, and when added, they give me a negative 4. So it's going to be 2 and 2, but both of them negative, right? So we're going to open two parentheses. And so I'm going to put x and x on each parenthesis, and then minus 2 and minus 2. Now, if we take a look to these factors, we can realize that the same factor is being repeated 2 times. So we can write it like this. Okay? So let's go ahead and solve for x. So we're going to set m equal to 0 and solve for x. So x is equal to 0. X minus 2 is equal to 0, and if I solve for x, it gives me x equals to positive 2. What can we say about this factor, about this 0, x is equal to 2? That, if you notice, that one has a multiplicity of 2, meaning that the factor is repeated 2 times itself. So that's what it means by the multiplicity. So we're going to say that this one has a multiplicity of 2. This factor repeats only once. Right, that's what we see because it's only x to the first power. So that means that this factor has a multiplicity of 1. When a factor has a multiplicity of 1, then we're going to say that the graph crosses the x-axis at 0. Crosses, and I show you what crosses means. Now, since this one has a multiplicity of 2, that one is an even multiplicity. This one was an odd multiplicity. That's why it crosses the x-axis. Multiplicity of 2, this one is an even multiplicity, and anytime a function has an even multiplicity on a 0, then we can say that the graph touches the x-axis and turns around at 2. And those are my solutions for this problem. This is one of my zeros with multiplicity of 1, and it crosses the x-axis at that 0. This is my second 0 with multiplicity of 2, and it touches the x-axis and turns around at that 0. Now, for the next problem, we're going to talk about the intermediate value theorem. Now, on this one, it's basically going to tell us the following. So it says, let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c is equal to 0. So this basically tells us the following. If I have a polynomial function in which for any two values of a and b, x equals a and x equals b, it tells me that f of a and f of b have opposite signs, meaning that one of them is positive and the other one is negative. Okay, so let's say this is one point and the other point is right here. So according to the definition, since this is a polynomial function what we are talking about, remember the characteristics of a polynomial function, smooth and continuous. What does it mean by smooth? It means that it contains rounded curves, and continuous means that it keeps on going, so there's no breaks, there's no stops. So in order for this graph of this polynomial to get from this point to the other point, what must happen is that it must cross the x-axis at least once between a and b. That's what this definition is telling us right now. So And at least means that it can cross it more times, but one is at least, in order for it to get from A to B, it has to cross at least once the x-axis. That's what it must happen, since the values of y, one of them is positive and the other one is negative. So what we need to prove here is, in order for me to find out if there is a 0 between any two given values of x, I need to find the y values of each and determine whether, by looking at the signs, if both of them have the same sign, then it doesn't have to, the graph of the polynomial doesn't have to cross the x-axis to get from one point to the other point. But if the signs of the 2 points, the values of y, have opposite signs, then it is true that it must cross the x-axis to get from one point to the other point. Okay? So let's talk about that in this problem here. So we're going to use the intermediate value theorem to show that the polynomial f of x equals 2x to the 4th power minus 10x squared plus 7 has a real 0 between -2 and 0. So we're going to start by finding the y values at both locations. When x is equal to -2, we're going to find the y value by substituting it into the function. So f of -2 equals to 2 times -2 to the 4th power minus 10 times x, which is -2 squared, plus 7. Likewise, we have to find the y value when x is equal to 0. So it's f of 0 equals 2 times x to the 4th, which is 0 to the 4th power, minus 10 times x, which is 0 to the 2nd power, plus 7. So the first one, if I evaluate it, -2 to the 1st power is 16, and 16 times 2 is going to be a 32. 2 to the -2 to the 2nd power is 4, times -10 is minus 40, and then plus 7. So 32 minus 40 is -8, plus 7 is -1. The second one, 0 to the 4th power is 0, times 2 is still going to be 0, minus 0 to the 2nd power is 0, times -10 is 0, and then plus 7. Those three are going to give me 7. So what inference can we make out of this? You see the values of y for each of those values of x, one of them is negative and one of them is positive. So that means that in order for the graph to go from this point to that point, it must cross the x-axis between -2 and 0 to go from a negative y value to a positive y value. So we're going to say the following. Since f of -2 and f of 0, those are the values of y, have opposite signs, then we can conclude that there is at least one 0, meaning one x-intercept, one real 0 between -2 and 0, period. Since they have opposite signs on the y, then it must cross the x-axis at least one time between -2 and 0 to get from a negative y value to a positive y value. For the next and last concept of polynomial functions, we're going to be covering what is called the turning points of polynomial functions. Now, what is a turning point basically is, we discussed before the definition of relative maximum and relative minimum. So basically, that's what the turning points will basically represent. So if I have a polynomial function, let's say this is my polynomial, any point on which the function turns over, turns around, so where, in other words, anywhere that you have a relative maximum or minimum in the function, it is called a turning point. Now, the definition tells you the following, that any polynomial function with degree n has at the most n minus 1 turning points. At the most. What does it mean by at the most? Means that it doesn't have to be that many turning points. It could be less than that. So let's say if I have a polynomial of degree of 5, that means that that polynomial has at the most 4 turning points, but it could be 3 turning points, or it could be 2 turning points, or it could be 1. Okay, so that is going to be the maximum number of turning points that the function could have. So now we're going to get into basically the last part of the section, which is a strategy on how we can graph polynomial functions. Okay, so on this strategy we're going to be finding the following items. Number one, first thing that needs to be found is we need to find the end behavior of the polynomial function. If it rises on the right, falls on the left, and so on and so on. So whatever the end behavior is, use the leading coefficient to find the end behavior. Number two, we need to find the x-intercepts by setting the y equals to 0, and then we have to say the multiplicities and if it touches or crosses the x-axis. Number three, we have to find the y-intercept by setting the x equal to 0. We have to determine the symmetry. To find the symmetry, there's two types of symmetries, y-axis symmetry and origin symmetry. Remember, in order for a function to have y-axis symmetry means that if I replace every x with a negative x, if the equation doesn't change at all, then it is symmetric with respect to the y-axis. If when I replace every x with a negative x and my equation, my function, changes all of its signs, that is when the function has what is called origin symmetry. And origin symmetry, we talked about it, it means that it reflects over the y and x-axis simultaneously. And number 5, we're going to determine the maximum number of turning points on the function by using the formula n minus 1. Remember that a function has n minus 1 turning points. Okay? So let's go ahead and get started with some of these questions. We're going to begin with this question right here. We're going to use the 5-step process described in the textbook to sketch the graph of the following polynomial function. F of x equals x to the 4th power minus 36 x to the 2nd power. So the first thing we got to do is we need to find the end behavior of this function. So to determine the end behavior, we're going to look at the degree and the leading coefficient. Right here, the degree of this polynomial, it is an even degree, and the leading coefficient of this polynomial, it is a 1, meaning that it is a positive leading coefficient. So if it is a positive leading coefficient and an even degree, the shape of the polynomial is going to be kind of like a U shape, which means that both of the endpoints, both ends of the graph, the left and the right end, both of them will go up. So we're going to say the following. So for the end behavior, we're going to say that the graph of f of x rises on the left and rises on the right. So that is my first solution, my first answer to the 5-step process. Number 2. Second item that we have to find, it is going to be the x-intercepts, the multiplicities, and state whether the graph crosses or touches the x-axis at each one of those intercepts. So to find the x-intercepts, what we have to do is we're going to set the y, which is the f of x, equals to 0. And then we're going to factor this polynomial. So to factor this out, the first thing we're going to do is, remember, we need to find the greatest common factor, if there is any. So which in this case, x to the 4th and 36x squared, we can factor an x squared. So I'm going to divide out the x squared and I'm going to put that x squared in the front, on the outside. And what we're going to have left is x squared minus 36. Next, now you see that we need to determine what is the best strategy for us to use right here to factor this binomial. Now, this one contains two terms. Anytime a polynomial contains two terms, then it could be a difference of squares, sum of cubes, or difference of cubes. In this case, this one is going to be a difference of two squares, so it looks in the form a squared minus b squared. So all we gotta do is find a and b, which is a is going to be something that when squared gives me x squared, which it would be x, and b would be something that when squared gives me 36, that would be 6. So now we have it in the form of a squared minus b squared, and the factors of this polynomial would be in the form of a plus b times a minus b, where a is x and b is 6. So it's x plus 6 times x minus 6. And then we don't forget to bring down the x to the second power, which is my GCF. Now, to finish the x-intercepts, we're going to set each factor equal to 0, and we're going to solve for x. So that's x equals to 0, this one is x equals to negative 6, and this one is x equals to positive 6. Now, if we look at this equation, how many times does the x minus 6 appear on this equation? Only once. How many times does the x plus 6 appears on this equation? Only once. So automatically we can say the following, that these two zeros have a multiplicity of 1 because they appear only once on the equation. So if it has a multiplicity of 1, keep in mind that multiplicity of 1 is an odd multiplicity. So that means that the graph of the function crosses the x-axis at each one of those two. So we're going to say the graph crosses the x-axis at negative 6 and positive 6. Now, if we look at this 0, x equals to 0, that one has a multiplicity of 2 because you see that that x appears 2 times in the equation. It is x squared, right? So it's the same thing as saying x equals to 0 and x equals to 0 2 times. So that means that this one has a multiplicity of 2. When a 0 has a multiplicity of 2, then that's an even multiplicity. And when you have an even multiplicity, we can say that the graph touches the x-axis and turns around at 0. And this is the information we need to provide about the x-intercepts. Number 3. The third item we have to find here is going to be the y-intercept. To find the y-intercept, all we have to do, we're going to go to the function f of x equals x to the 4th minus 36x squared. All we got to do is replace every x with the 0. So it's going to be 0 to the 4th power minus 36 times 0 to the 2nd power. So that's going to give us a 0 minus 0 squared is going to be 0 times 36 is still 0. So the y-intercept is going to be 0. Make sure you write your y-intercept as an ordered pair, so it would be the point 0, 0. Okay. Now, fourth item that we have to find here is going to be determine if this function has any type of symmetry. So to determine if there's any type of symmetry, what we have to do the f of negative x test. If the equation changes the signs, it's symmetrical with the y-axis. If the equation stays exactly the same, then it is symmetrical. If it stays exactly the same, it is symmetrical with the y-axis. If it changes all of the signs, it is symmetrical with the origin. So we're going to redo the negative f of negative x test. So I'm going to replace every x with a negative x. So it's negative x to the fourth power minus 36 times negative x to the second power. So negative x raised to the fourth power is going to give us a positive x to the fourth. Then negative x to the second power is going to give us an x squared positive. But then when we multiply times negative 36, it's going to end up being negative 36x to the second. And as we can see, if we compare this equation to the original, they are exactly the same. So when you get the same equation back, that means that this function is symmetrical with respect to the y-axis. So we're going to say that this function has y-axis symmetry. Last but not least, number 5, we have to determine the maximum number of turning points. And that can be found by subtracting the degree minus 1. So that means the degree in this function is a 4. So 4 minus 1, it's going to give me 3. So what does this mean? That this function is going to turn at the most 3 times. So now we're going to put all this information together to sketch the graph of this polynomial. So let's go here and let's put it all together. So we got that the x-intercepts of this function are 0, negative 6, and positive 6. So it's going to cross the x-axis at negative 6, it's going to touch the x-axis at 0, and it's going to cross the x-axis at 6. Remember, right here it's going to cross, right here it's going to touch, and right here it's going to cross. That's what we have right here. Touches at 0 and crosses at negative 6 and 6. Now, my y-intercept, it is 0, 0, so it is right in the middle. So it's that same point. Then, it has y-axis symmetry, so that means that it's going to look the same on both sides of the y-axis. So I'm going to put a little dotted line to remind you right here that the graph is going to look exactly the same on both sides of the y-axis. It's going to be symmetrical, left and right. So now if we look at the end behavior, at the end on the left side it's going to rise, and at the end on the right side it's going to rise. So it's going to rise on both sides. So now we can go ahead and connect the graph without taking off the pencil from the paper. Remember, once the graph gets close to this number, it is going to cross the x-axis. So it's going to go over to the bottom of the graph. Okay? Then we're going to make one turning point. So right now I'm not interested in how low or how low is this curve going to go. So we're just going to make a little turning so we can go back to this point right here, anywhere. Now, what's going to happen when it gets close to 0? The graph is going to touch the x-axis, but then it's going to turn back down, turn around. And then it's going to make another turn to basically go back to the last point right here. And what happens when it gets to the 6? The graph is going to cross the x-axis to the other side, and then it's going to connect to the other end. This is approximately what the graph of the function will look like. Now, the only thing that we're not interested at this moment is basically how low is this curve going to be. So it could be that it goes a little bit lower, it could be that it goes lower. Again, right now all I'm doing is a sketch based on the intercepts, which is the x-intercepts, the multiplicities, if it touches or crosses, the y-intercept, and the end behavior. And of course the symmetry and the number of turning points. We're going to make one more sketch of a function right here. We're going to create the sketch of this function. This one says, use the 5-step process described in the book to sketch the graph of this function. So, first thing that we're going to determine on this one again is we're going to determine the end behavior of the graph. Now for the end behavior of this one, Now we gotta be careful because this function, it is in factored form. What does that mean? It means that we need to first of all add the exponents of the x's, because when you multiply these parentheses back to put it in standard form, you're gonna have to add the powers. So you see that this one is gonna have a power of 2, right? Because of the second power here. This one has a power of 2. So when I multiply them and then times the -4, this is going to be my leading term. -4 x to the 4th power. I'm just interested right now in the highest power. So what does that tell us? That since we have a leading coefficient that is negative, and we have a degree that is even. First of all, if it has an even degree, it has the shape of a U. But if the leading coefficient is negative, it's gonna open downward. So what we're gonna see is that both ends of the graph are going to fall. So we're gonna say the following: end behavior. We're gonna say that the graph of f of x falls on the left and falls on the right. Period. Second, now the next thing we're going to find is the x-intercepts and their multiplicities, and if it touches or crosses the x-axis. So, for the x-intercepts, so to find them, the first thing we have to do is we have to set the y on this function, set the y equals to 0, and then we factor and solve for x. Fortunately, right here we don't have to factor because it is already factored. There's only one expression that must be factored, which is the x squared minus 9, because that's where x squared minus 9 is differences of squares. So this is a squared, which is x squared, minus b squared, which is 3 squared. So the factors for this parenthesis is x plus 3 times x minus 3, which is a plus b times a minus b. And then of course this parenthesis square and the minus 4 in the front. So what happens, what do we get if we solve for x? This is going to give me x is equal to 1. This one is going to give us x equals to negative 3. And this one is going to give us x equals to positive 3. And if we look at these zeros right here, we can realize that x plus 3 appears one time on this equation. X minus 3 appears only one time on this equation. What does that mean? That both of these zeros have a multiplicity of 1, which is an odd multiplicity. And anytime we have an odd multiplicity, that means that the graph crosses the x-axis at negative 3 and 3. Now what can we say about this factor, x minus 1? That one is repeated 2 times because it has an exponent of 2. That means that it has a multiplicity of 2. So we're going to say that this factor has a multiplicity of 2, meaning that since it is an even multiplicity, the graph touches the x-axis and turns around at 0. I mean at 1. It touches the x-axis and turns around at 1. And this is the zeros and their multiplicities. So we got 2 answers so far. Next, what we are going to be finding next is the y-intercept. So to find the y-intercept, we're going to go to the function f of x equals negative 4 parentheses x minus 1 squared times x squared minus 9. And what we have to do to find the y-intercept, we have to replace every x with a 0. 0 minus negative 4 parentheses 0 minus 1 squared. In another parenthesis is 0 squared minus 9. So 0 minus 1 is negative 1. 0 squared is 0 minus 9 is negative 9. Now let's square that parenthesis. So negative 1 squared, it's a positive 1. So then if I multiply these three values, negative 4 times 1 times negative 9, it's going to give me a positive 36. So that means that it crosses the y-axis at 0, 36. That's what my y-intercept is going to be. Now, for the next item, we are going to be finding the symmetry. Now, the symmetry right here in this function is going to be a little bit more difficult for the reason that this polynomial, it is in factor form. So what I would recommend for us to do is that we multiply all of these factors back together and then we do the negative x test. So that x minus 1 squared means x minus 1 times x minus 1, and whatever we get from that, we're going to multiply it by x squared minus 9 and then times negative 4. So let's multiply the factors really quick. So these two, if I multiply these two, x times x is x squared. Then this is going to be a minus 1x, and minus 1x, which is going to be minus 2x. And negative 1 times negative 1 is positive 1. And then times negative 4 times x squared minus 9. Now, let's multiply these two parentheses now. X squared, I'm going to put it right here. X squared times x squared, it's going to be x to the 4th power. So I'm going to put the negative 4 on the outside first. And that's going to give us x to the 4th power. X squared times negative 9, it's negative 9x squared. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 9 is positive 18x. So positive 18x. And then we're going to multiply. The 1 times x squared is just going to be x squared. And the 1 times negative 9 is negative 9. And then we're going to combine the like terms and then multiply everything times negative 4. So we're going to have this. The like terms we can combine are the x squares. This one and this one. Everything else is going to stay separate. So it would be x to the 4th minus 2x cubed. Then negative 9 plus 1, it's going to be negative 8x squared plus 18x minus 9. Everything times the negative 4. So that would give us negative 4x to the 4th power plus 8x to the 3rd power plus 32x squared. Then if we multiply this one times 4, it's going to be minus, it is a 72, x, and then plus a 36. Now, I just want you to check on something, that on this polynomial, if I replace every x with a negative on this polynomial, what we're going to get is the following. Negative 4 times x, which is going to become a negative x to the 4th, then plus 8 times x, which becomes a negative x to the 3rd power, plus 32 times negative x to the 2nd power, minus 72 times negative x, plus 36. Now, if I do the whole math right here, if I raise this to the fourth power, it's going to be positive x to the fourth times negative 4 is going to result in a negative 4x to the fourth power. So right here to begin, f of negative x equals to negative 4x to the fourth power. If I raise this to the third, it's going to end up as negative x cubed times 8 is negative 8x cubed. Then negative x to the second would be positive x squared times 32 is going to be positive 32x squared. Negative 72 times negative x is positive 72x, and then plus 36. Then we have to compare this to the original function. Can we say that they are the same? No, because not all the signs are the same. Can I say that all of the signs change? No, because not all the signs change. So what does that mean? That this function has no symmetry. And the last item for this function is going to be number 5. We're going to determine the maximum number of turning points. And the formula for the maximum number of turning points, it is going to be n minus 1, where n is the degree. What do we say the degree of this function is? As you can see here, is degree of 4. So it's going to be 4 minus 1, which means that this function has at the most 3 turning points. Remember, that doesn't mean that it's going to turn 3 times. It could be turned less than that. Okay, so let's go ahead and put everything together in the graph. So the x-intercepts are 1. I'm going to graph those x-intercepts. Negative 3 and positive 3. So 1, negative 3, and positive 3. Those are my x-intercepts. Now, my y-intercept, as you can see, it was 0, 36. Now, that one is a little bit high, so what I am going to do, let's pretend that the 36 is going to be already here. So I'm just going to put it right here. Let's pretend we already reached the 36 at this point. Okay? And then, what do we know about the end behavior? What happens on the left end and the right end? Both ends are going to go down on this side and down on the other side. And as we already specified, there is no symmetry on this function. Okay? So, how do we connect this? Let's go ahead and put everything together, keeping in mind what happens at the intercepts. What does it tell me what happens at negative 3? We said that the graph touches, at negative 3, the graph crosses the x-axis. What did we say about right here at 1? The graph touches the x-axis and turn around. So right here I'm going to put a T. And what happens back at this 3? It crosses the x-axis. So we're going to put everything together. So right here, the graph, it is going to cross the x-axis and to the other side. Then, how is it going to go? We already know that it's going to reach my y-intercept right here at 36. And then what's going to happen? It's going to go down. So I'm going to have one turn somewhere in there, right? Then it's going to go back to this location. It's going to go back to the 1. And what is going to happen? Let me just make it more accurate here. So it is going to go back right here to the 1 until it hits the 1. And what happens when it gets close to 1? The graph, it is going to touch the x-axis right here and is going to turn around. And then it's going to go back down. I don't care how high does it go, so let's just make a turn. And what happens at 3? It is going to cross the x-axis to the other side. This is kind of what the sketch, similarly of what it would look like if graphed accurately. Okay, it is not 100% accurate because of these maximums and minimums. We don't know exactly how high they go, but this is an estimate of what the graph will actually look like. All right. Last question that we're going to do on this review, on this section, it is going to be do the same thing on this function. So the first step in the process again is that we need to determine the end behavior. So to determine the end behavior, what we have to do is we have to look at the degree and the leading coefficient. As we can see right here, the degree of this polynomial is 3, which is an odd degree. That's what we have here. And the leading coefficient right here in the front, it is a 1, which is a positive leading coefficient. So if it's an odd degree and a positive leading coefficient, we're looking at like kind of an S shape that increases from left to right. So basically the end behavior is that the graph falls to the left side and it rises to the right side. So we're going to say the graph of f of x falls to the left and rises to the right. Now the second question that we need to answer here would be find the x-intercepts and the multiplicities and state whether the graph crosses or touches the x-axis at each one of the intercepts. So we're going to go to the function f of x equals x to the third plus 3x squared minus x minus 3. In order for me to find the x-intercepts, what we have to do, we have to set the f of x, which is the y, equals to 0. And then what we have to do is factor. Now, if we look at this polynomial entirely, there is no GCF, right? There is no GCF between all the factors, all the terms, so the GCF is 1. So, in order for us to factor a polynomial with 4 terms, we have to factor it using grouping. So, let's go ahead and use grouping right here. So, we're going to put these first two terms in one group and these 2 terms in another group. Okay? And then we're going to take out the greatest common factors. Now, from these 2 groups right here, we can factor an x squared from both of them. So, we're going to take out the x squared from these 2 groups, from these 2 terms. And if I take out the x squared, we are left with an x plus 3. Now, from these 2 terms on the other group, the negative x and negative 3, the only factor is 1. But since there's a negative in the front, then we have to factor the negative. So it has to be a negative 1. So then if I factor the negative 1, the signs are going to change to x plus 3 as well. Then what can we see here is that once again both of these have a greatest common factor of x plus 3 again. Right? So we're going to take out that x plus 3. And if I take that out, then what are we left with? We are left with the x squared minus the 1. Now remember that in this polynomial, we can use the idea that we can factor further. Why? Because this polynomial, we still have an x squared minus 1. We still have a square. So we can still factor that polynomial. This one is a difference of 2 squares. We can write it like this. A squared minus b squared, which is x squared minus 1 squared, equals x squared minus 1. Right? So this is a and b is 1. So the factors for this will be a plus b, which is x plus 1, times a minus b, which is x minus 1. And then we're going to bring this factor down, which is x plus 3. So we're going to set m equal to 0 and solve for x. So this is x equals to negative 3, x equals to negative 1, and x equals to positive 1. What can we notice about all of these factors is that all of them appear only one time each. What does it mean by that? It means that all of these zeros have a multiplicity of 1. Since that is an odd multiplicity, what happens when a 0 has an odd multiplicity? The graph crosses the x-axis at each one of them. The graph crosses the x-axis at -3, -1, and +1. So these are my solutions for the x-intercepts. Number 3, we're going to find the y-intercept. Now, to find the y-intercept, we have to set on this function, we have to set every x in the function equals to 0. Okay, so we're going to set every x equals to 0, so we're going to get 0 to the third power plus 3 times 0 to the second power minus 0 minus 3. So right there, this is going to be a 0 plus a 0 minus 0 minus 3, which gives me a y-intercept of -3. So if I write the y-intercept as an ordered pair, will be the point 0, comma, -3. Number 4, how do we determine the type of symmetry that this function has? To determine the type of symmetry, what we have to do is we have to change every x in the function to a -x. So we're going to replace every x with a -x. So if I do that, let's go ahead and evaluate. And let's remember this, let me give myself some space. So if I raise the -x to the third power, it's going to give me a -x cubed. So my first term right here, it's going to be a -x cubed. If I raise the -x to the second, it's going to be +x squared times 3 is going to be +3x squared. Negative times -x is going to be +x, and then the -3. Now we have to ask ourselves the question, are these two functions the same? No, because some of the signs change. Now, did all of the signs change? No. So that means there is no y-axis symmetry because they are not the same, and it doesn't have origin symmetry because not all the signs change. So we have no symmetry on this function. And the last item on this problem is going to be determine the maximum number of turning points. And to determine the maximum number of turning points, the formula is going to be the degree minus 1, where in this case the degree is a 3. So 3 minus 1, it's going to give me a 2, meaning that this function is going to have at the most 2 turning points. Let's put everything together in the graph of this function. So first of all, let's plot the x-intercepts. It crosses the x-axis at -3, -1, and +1. So, and it's going to cross at each one of them. So I'm going to put crosses, crosses, and crosses. Okay. Now, what's going to happen next? The y-intercept is 0, -3. So here's my y-intercept down here. Then what happens next? Okay. Then we have to put the end behavior. What does the end behavior tells me? That it falls on the left side. So that means that on the left side the graph is going to go down, and on the right side it's going to rise, meaning that it's going to go up. Okay. And then there is no symmetry, so that's fine. And remember that the maximum number of times that you can turn the graph, it's going to be 2 times. So when I go to this point, it's going to cross the x-axis. Then we're going to make the first turn. Then when the graph goes to this point, it's going to cross the x-axis. Then right here, after my y-intercept, I'm going to make my second turn, and that's the last turn I can make. And when the graph gets to this intercept, it's going to cross the x-axis, and it's going to connect to the other end. This is similarly very close to what the graph of this function will actually look like. The only thing that is not 100% accurate, like I told you, is this maximum, because we don't know how high that goes. We're just estimating it. We're just rounding it right here. We're close enough. All we care about is what the shape of the polynomial will actually look like. Basically, these are all the concepts that must be covered for this section, section 3.2 on polynomial functions.